Okay, let's go and get started today. Today we're going to talk about Chomsky Normal Form for context-free grammars. And essentially what a normal form is, let's talk about that first, and then we'll get into the specifics of what Chomsky Normal Form looks like. But a normal form is essentially a form for representing something, in this case a grammar, that it places some sort of restrictions on the format of the representation without really restricting what can be represented. So in other words, it's basically saying when you represent this grammar, the rules for the grammar, the productions are all going to look like some limited set of forms. And because it doesn't overly restrict what we can represent, that means we could take a grammar that's not in that form and then convert it to that form. And the normal forms can be useful for a number of reasons. We're going to see one of those today with Chomsky Normal Form. So let's go ahead and get started and take a look at what Chomsky Normal Form is, and then we'll talk about what the reason for putting things into that form is toward the end. Okay, so first off, the way Chomsky Normal Form works, it's a context-free grammar, but there's a restriction on the way we make the productions. And the way that we make those productions is they all have to be in the form of one of two possibilities. Either A produces A, where this is a variable, A is a variable, and this other thing on the right-hand side is a single terminal. So in other words, a variable can produce a single terminal, or a variable can produce two other variables. That's the only kinds of forms we want. So every production will have variable producing single terminal, variable producing two variables. That's it. We're not allowed to have anything else. And since this is a normal form, that doesn't necessarily restrict what we can represent. There is one exception. The one exception is there's a restriction is that lambda cannot be part of the language for it to be in Chomsky Normal Form. Now, there is a way to still take languages that have lambda in them and still represent them where you have this S production, the start production, going to some new production, like let's say S prime, and then you have S also going to lambda, and then S prime is all in Chomsky Normal Form. But for Chomsky Normal Form itself, notice that back here with the two rules, there's nowhere we can get a lambda. It's either a variable producing a terminal or a variable producing two variables. No way to get a lambda out of that. So that's the only restriction that we have, is that lambda cannot be in the language, but every other context-free grammar could be converted into Chomsky Normal Form as long as lambda is not in the language. If lambda is in the language, we have to factor that lambda out and have that handled in that start production, and then everything below that could be Chomsky Normal Form. So what we would like is to say, have a method for converting a context-free grammar into Chomsky Normal Form. All right, so let's look at the conversion process. So the conversion process essentially has 4 steps. And the first step is to do a little bit of work on the grammar using those manipulations we saw before. In other words, we want to get rid of useless productions because they're, well, useless. So we get rid of useless productions, we get rid of unit productions, and we get rid of lambda productions. So if we get rid of all lambda productions, all unit productions, all useless productions, then that's going to leave behind this grammar that is free from all of those things. And now we're ready to turn that into Chomsky Normal Form. So the first step of what we do here is we make new variables for every terminal that's in our set of terminals, or every terminal in our alphabet, every symbol in our alphabet. We make a special variable specifically for that one. So here's, like, for example, the variable t sub a goes to a, t sub b goes to b, and so forth. So every symbol in our alphabet, we make a special variable for that producing that. And you'll notice that these now all fit that first rule type here, variable producing a single terminal. And since we've done that for every variable, or for every terminal in our alphabet, every terminal in T, variable producing single terminal. Now this subscript A is not some separate notation. This is just saying this is the terminal variable for A, this is the terminal variable for B, and we do that for all of the symbols in our alphabet. Now after we've done that, we're ready for step 3. And what step 3 is, now we replace all the terminals on the right-hand side of the original productions with the new variables that were created in 2. In other words, wherever I see a terminal on the right-hand side, I'm going to replace that with that variable that we had here, t sub whichever one it is. So after we're done with this step, you'll notice that means the right-hand side of those productions will now no longer have any terminals in them, except for these new ones that we created here. The rest of them will all be strings of variables on the right-hand side. So that brings us to step 4, which we say any production that has a right-hand side that has a string of more than 2 variables is going to be now separated by introducing a new variable and then dividing the production into subsequent substeps. So this will make more sense when we look at our example here. So let's go and take a look at that. So in our case, the example, let's start off with this grammar. So this grammar, S produces A produces AC, A produces BB, B produces BBA. Now, is this already in Chomsky normal form? And the answer is no, because we need to have every production either have a variable with a single terminal or a variable and 2 variables. And none of these actually fit that. This has 3 symbols, one of which is a terminal, 2 variables before that. That doesn't fit any of the form. This one doesn't fit the form. This has a variable and a terminal. This has 2 terminals. That doesn't fit the form. And this one doesn't fit the form because we have 3 symbols, 3 terminals. None of these productions in this grammar fit either of the 2 possibilities that we're allowed to have for Chomsky normal form. So let's go through our process. So process 1, remove unit productions, useless productions, and lambda productions. Well, first off, there are no unit productions. There are no lambda productions. And there are no useless productions. So this step 1 on this one was easy. It's already done. It's already in a form where it doesn't have unit productions, useless productions, or lambda productions. So we're good there. If we did have one of these, we would just go through the method that we learned 2 classes ago to get rid of those. But this case, don't have to worry about it. So now we're on to step 2. Make the new variables and productions for all terminals in our alphabet or in T. And T in this case is A, B, and C. So we're going to make new variables. The T variable for A produces A. T variable for B produces B. T variable for C produces C. So now we're on to step 3. Replace all the right-hand side terminals. So any production here where I see a terminal, replace it with that variable. So in this case, for example, that A at the end of this production for S, that's going to become T sub A. This C is going to become T sub C. This T or BB is going to become TB, TB. And then this BB, BBA here is going to become TB, TB, TA. All right, so we go through that replacement, plug all those in. There's the TA being substituted for the A. Here's the TC being substituted for that C. Here's, actually there's a slight mistake here. This needs to be TB, here. Let me fix that real quick. B, TB. Okay, that looks right. That might have rippled down to the next slide. Let's look. Now, so after we do that, we're now ready for step 4 where we split those up. Well, let's identify which ones need to be split. So first off, these ones are all okay because I have a variable producing a single terminal. But S has 3 variables, not 2. So that one needs to be split. Now let's look at A. A has variable, variable. That one's okay. And this production, TB, TB, that's variable, variable. So that one's okay. But this one for B also needs to be split because it's got 3 variables in it. So now let's look at how we're going to split that. So to split that, looking at here, hold on a second. I need to fix this and oops. I said that might have rippled through the next one, so let me fix that too. So that's TB, TB. Okay, so now we're good on that one. Okay, so that one, those 2 are the ones that need to be split. So let's start with that first one. And I guess while I'm here and while I remember it, let me fix this one too. Okay, so we're going to split this one. So this has 3 variables. How do we split it? Well, we're going to say S produces A, but we're going to now put a new variable, S prime, on the end of that. And then S prime is just going to be the second 2. So you can see how this works. We make the A, and then we put a variable that's going to now represent these 2 things that came after that A. So S prime is B, T sub A. And now we have 2 of them where we have a variable on the left two variables on the right. S prime, variable on the left, two variables on the right. So now that we've divided that, now we have something that's in Chomsky normal form for that one. Now, we said there was one other one that needed to be divided. And again, while I'm thinking about it, let's fix this. And the other one that needs to be divided is this one down here. And unfortunately, I've got to fix this on all these pages. All right, so how do we fix this one? Well, this has three variables. We're going to do the same thing. So we're going to divide that up into the first variable and then a new variable for these two. And of course, I still need to fix this. Sorry about that. All right, so now notice this one is getting divided up into TB, B prime, and then B prime is now the second two, which is TB, TA, TB, TA. So now if I replace this one with these two and this one with these two, now everything will be in Chomsky normal form. Let me fix this. Fix. That. All right, so now we should be good. We replaced the S as A, B, T, A with these two, and now are those two. We've replaced this B as TB, TB, TA with TB, B prime, TB, TA. And now if you look at that, look at all of the productions in this grammar, they all are now in one of those two forms. Variable, two variables. Variable, two variables. Variable, two variables. Variable, two variables, and so forth. Or, then we get down here, variable, terminal, variable, terminal, variable, terminal. These are always single terminals. So now we have that, and it's in Chomsky normal form. And one of the questions that comes up is like, well, why did we do that? And let's go back and look at that. So we started with this thing that only had three productions, or three variables, I mean, and four productions. And now we have this thing that has 1, 2, 3, 4, 5, 6, 7, 8 variables and 8, 9 productions. So it looks like we made it more complicated and convoluted. So the question would be like, well, why would we ever do that? Why would we take something like this and turn it into something like that? And there actually turns out there's a really good reason for that. And so the answer to why we're doing that is think about the two types of productions. It's either a variable producing a terminal that ends things, or it's a variable that goes into two variables or branches into two different variables. So if you think about a binary tree structure for storing things in like a binary tree in memory, binary trees have two types of nodes. They have a branching node that has like a left pointer and a right pointer, or a left branch and a right branch, or they are at the end of a leaf node where it's just a piece of data that's at the leaf. And so notice that this perfectly fits that. This variable producing a terminal, that's a leaf. Variable producing two variables, that's a branch that is guaranteed to only branch two ways. It'll branch to one side and the other side, and then this thing could either end or have another branch below. So the reason for this is this maps perfectly onto a binary tree data structure, and that means that we could create a grammar that fits very nicely onto a binary tree, and that can help us in a number of ways. It can help us implement something that then stores the parse tree in a binary tree. It could also help us with certain kinds of proofs for proving how many branches deep we have to go into something to find some solution. But notice it can simplify things because it's makes the tree very uniform. It's either a branch or it's a leaf. And again, we can turn any context tree grammar into mapping onto something like that as long as it does not have lambda in the language itself. So it does not restrict the languages other than that lambda. Okay, now, one more thing that I want to cover today that's not Chomsky normal form. And we're going to use this next class as well. But sometimes when we're parsing, it can be made easier by always having a terminal in the first position. So here, for example, A produces AX, where this lowercase a is a terminal. And you'll notice that that was true for that predictive parsing that we did last time, where if I know what terminal is coming up, I know that, and I know what my input or I know what my input coming up is, I know what that next symbol is, and I can look at all of my productions and I can eliminate some as that's not a path because I know that doesn't match a symbol, and other ones I can say that could be a path because it has that symbol on it. But notice that one of the things that I want to point out here is that if we have, like for example in this grammar down here, that one has a terminal at the beginning, the second one does not, the third one does, and then down here both of these do. So is there a way we could manipulate this grammar to get rid of that variable coming first? And in this case, the answer is yes. And the reason being that we can basically just notice that production starts with that variable, doesn't start with a terminal. So how can we fix that? And the answer is through substitution. So for example, this starts with an A, the variable A. Well, if I just go down and look at what A could eventually produce, this right-hand side, I could just substitute those in for that and have every possibility. So since A has two productions, two right-hand sides, I could take this and take that one out, delete that, and replace it with AA in place of that A, or B in place of that A, and get productions that now have the same thing. And then those have, since those both start with this terminal, now we've gotten rid of the case where we had something that started with a variable. So here's the example where we did that. We took this AA out and we replaced it in the two possible ways with that one substituting this. I color-coded these to make it a little easier to see. So I stuck the AA in for the A there, and I stuck the B in for it there. And now if I look at this grammar, now I don't have that problem anymore. Every one of these starts with a terminal, which can act as a signpost or guidepost for our something like a recursive descent predictive parser. And there can be other advantages to that too. That means every time I use a production, I'm consuming a symbol. I'm always making progress through my input if I can put a grammar into that form. Now, we're going to look at another normal form next class that kind of takes this to an extreme. But before we do that, I want to talk about substitution just a little more in a more general sense. So substitution in a general sense, any variable we could do that with any variable, not just ones that are at the beginning of a production. It's right-hand side. So, for example, in this case, we have A produces x1, where x1 is a string of any variables and terminals. x2 is a string of any variables and terminals. And let's say we have a variable in there, B, that's somewhere on our right-hand side. And as long as that variable is not the same as this one, as long as those are different variables, we could always do a substitution on this. So here's variable B with all of its right-hand sides, whatever those happen to be, all the productions who have right-hand sides for variable B. And this could be a string of anything, could be lambda, could be anything. But we can always perform a substitution for this and get rid of the variable B in this production A by just going through and replacing all of these productions that look like this by deleting that, remove it from the grammar entirely, and then add new productions that now have all of these Y's substituted in. But we need every combination. So if we have Y, we're going to have X1 and then followed by Y1 plugged in for B, because that's one of the things B could have done. And then X2, and then X1 with one of the second thing that B could have done, Y2, X2, and so forth, all the way through all of them up to Yn. So X1, Yn, X2. So we could always do that substitution like that, no matter what variable it is in any production on the right-hand side. And that's going to be useful to us later on for manipulating things. So substitutions can be done to manipulate any variable in the grammar and get rid of it from the right-hand side of a production, as long as the left-hand side variable is not the same as the right-hand side. So we just replace the variable with each possible right-hand side of its productions. And that can be useful as a way to manipulate a grammar without changing the language it represents. So that will not change the language it's represented, but it is a way to change the form around. And that's going to be something that's going to be really useful for us next class when we look at this other normal form called Graybach normal form. And what Graybach normal form is, it's has its own uses, but it's going to force the grammar to have those terminals in that leftmost position like we talked about. And it's going to also put them into a hierarchy for us, which can be really useful for parsing things like we were looking at before. Okay, so that's it for today. The relatively short lecture. I would encourage you to go back and look over that conversion to Chomsky Normal Form. There may be a quiz on that. So I would encourage you to look at that. I'm not going to have a new quiz tonight or a new assignment tonight. I'll hold off on that until next time. But do look at how to convert to Chomsky Normal Form, because we'll probably have a quiz on that next class. And I'll try to get the other stuff graded and back to you before next class as well. All right, so that's it for today. Everybody stay safe, and hopefully I'll see you guys soon. Also, I don't know if I mentioned this or not, but the plan for this class is to have the final exam before, I think I mentioned it last lecture, but the final exam will be before you guys leave for break. So I'll have a study guide for that. We're running short on time for that, but it'll cover everything we've covered up to that point. So probably Chomsky Normal Form, Greibach Normal Form. But then there are going to be a couple topics that we're going to cover after Thanksgiving that won't be on the final that I think that you should be exposed to in having an automata class. And I apologize for the kind of chaotic nature of things this semester with COVID going on and with the video lectures and with stuff. But I guess the good news is you'll have a little bit less to study for the final exam. The bad news is that we're still going to cover it after the final exam, but you're not going to really have a test. You may have a little quiz on it. So everybody stay safe, and we'll talk next time. If you have any questions or problems, let me know. Send me a text message, send me an email. I'm happy to help.